In the early 20th century, scientists stumbled upon a strange and wondrous realm, the quantum realm. This is the world of atoms and the tiny particles within them, a world governed by laws entirely different from the familiar laws of classical physics. Quantum physics, the study of this microscopic realm, has revolutionized our understanding of the universe and opened doors to technologies that were once considered science fiction. Classical physics, which governs the macroscopic world, fails to explain the bizarre behavior of particles at the atomic and subatomic levels. Quantum physics emerges as a new set of rules that govern the interactions of these tiny entities, revealing a universe far stranger and more counterintuitive than we ever imagined. One of the most mind-boggling concepts in quantum physics is wave-particle duality. This concept suggests that particles like electrons and photons can exhibit both wave-like and particle-like behavior. This duality challenges our classical intuition, where objects are neatly categorized as either particles or waves. Imagine a beam of light passing through two slits. If light were purely a wave, we would expect to see interference patterns on a screen behind the slits, similar to ripples overlapping in a pond. Remarkably, this is exactly what happens. But here's the twist. When individual particles of light, called photons, are fired at the slits one by one, they still create an interference pattern over time, as if each photon is interfering with itself. This experiment demonstrates the wave-like behavior of individual particles. Another fundamental principle of quantum mechanics is superposition. This principle states that a particle can exist in multiple states simultaneously until it is measured. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle exists in a blurry combination of all possible states until we try to measure its specific property. This means that a particle can be in multiple places at once, spinning in opposite directions simultaneously, or even possessing different energy levels concurrently. It's only when we attempt to measure these properties that the superposition collapses and the particle chooses a single, definite state. The double-slit experiment mentioned earlier beautifully illustrates both wave-particle duality and superposition. When we don't observe which slit each photon passes through, they act like waves, creating an interference pattern. However, the moment we try to measure which slit a photon goes through, the interference pattern disappears, and the photons behave like particles. This mysterious behavior highlights a fundamental principle of quantum mechanics. The act of observation affects the system being observed. By choosing to measure a particular property, we force the quantum system to collapse into a specific state, losing its wave-like nature. Entanglement is perhaps the most bizarre and intriguing phenomenon in quantum mechanics. It describes a situation where two particles become linked, even when separated by vast distances. When one particle's state is measured, the other particle's state instantly knows and changes accordingly, regardless of the distance between them. Einstein famously called this spooky action at a distance, as it seems to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. Entanglement has profound implications for our understanding of the universe and has paved the way for groundbreaking technologies like quantum computers and quantum cryptography. Imagine a ball rolling up a hill. In classical physics, if the ball doesn't have enough energy to reach the top, it simply rolls back down. However, in the quantum world, particles can sometimes tunnel through energy barriers, even if they don't have enough energy to overcome them. This phenomenon, known as quantum tunneling, plays a crucial role in various natural processes, including nuclear fusion in stars and the functioning of our own DNA. Quantum tunneling also enables the development of technologies like scanning tunneling microscopes, which can image materials at the atomic level. Quantum computers leverage the principles of superposition and entanglement to perform computations in ways that classical computers can only dream of. While classical computers store information as bits, which can be either 0 or 1, quantum computers use qubits, which can be in a superposition of 0 and 1 simultaneously. This allows quantum computers to perform multiple calculations at once, giving them the potential to solve complex problems that are intractable for even the most powerful classical computers. Quantum computing is still in its early stages, but it holds immense promise for fields like drug discovery, materials science, and artificial intelligence. Although quantum physics may seem like a realm of abstract theory, it has already revolutionized our daily lives in countless ways. From lasers and transistors to medical imaging and GPS systems, quantum mechanics underpins many technologies we rely on every day. Quantum physics enables the development of lasers used in barcode scanners, CD players, and fiber optic communication. It also governs the behavior of transistors, the building blocks of modern computers and smartphones. Medical imaging techniques like MRI and PET scans rely on quantum phenomena to provide detailed images of our bodies. As we delve deeper into the quantum realm, we continue to unravel new mysteries and unlock the secrets of the universe at its most fundamental level. Quantum physics has challenged our classical intuitions and forced us to rethink our understanding of reality itself. The journey of quantum discovery is far from over. As we continue to explore this mind-boggling realm, we can expect even more groundbreaking discoveries that will reshape our understanding of the cosmos and lead to technological innovations beyond our wildest imaginations.